Hello everyone, this is the second video of my channel, but first I'd like to ask you, do you know where we are? And now is that better? Look at the flag. We are in Norway. And you know why we're here? We're here because of these two scientists from Norway, Peter Vasch, a chemist, and Kurt Gutenberg, a mathematician. Together they had discovered a mathematical relation that summarizes the composition of a reaction mixture at equilibrium. So you can understand better, take a look at this reaction. We have two molecules of sulfur dioxide reacting with oxygen gas. We have equilibrium arrows, and the product of this reaction is the sulfur trioxide. But now let's take a look at this table that we have 5 experiments using different initial pressures of the reactants and resulting in different equilibrium compositions for each case, as you can see in the table. For the gas SO2, for the oxygen gas, and for the gas SO3. A reminder, all of these reactions were taken at the same temperature, that is 1000 Kelvin. At first, we can't see an obvious relationship between those compositions, but Vasch and Gutenberg found some relationship though. Take a look at this parameter here, defined as K, that we call equilibrium constant. So we have the partial pressure of SO3 divided by the standard pressure, that's this P0. This expression is squared divided by the partial pressure of the gas SO2 divided by the standard pressure. Also, this expression is squared times the partial pressure of the gas oxygen divided by the standard pressure. The standard pressure is 1 bar, and we're using the partial pressure, the unity bar. So bar divided by bar is 1. So that means that the equilibrium constant is unitless. It doesn't have one unity. It's a dimensional number. And because the standard pressure is 1 bar, we can rewrite the equilibrium constant like this. That's easier for us to understand. Within the experimental error, as I've just said, the value of K is the same for all of the 5 experiments, regardless of the initial composition of the reaction mixture. For this specific reaction, K is 0.0413, and you can check that by putting the numbers here in this equation. This remarkable result shows us that K is characteristic of the composition of the reaction mixture at equilibrium at a given temperature. Remember, at a given temperature. If you change the temperature, it's not valid. It's also known as the equilibrium constant, as just said, for the reaction. The law of mass action, that is the topic of today, summarizes this result. It states that at equilibrium, the composition of the reaction mixture can be expressed in terms of an equilibrium constant, where for any reaction between gases that can be treated as ideal. So here we have something to remember. The equilibrium constant is the partial pressure of the products divided by the partial pressures of the reactants. For sure, we have to remember that we're talking about the equilibrium states. We have another reminder that we have for each partial pressure raised to a power equal to the corresponding stoichiometric coefficient in the balanced chemical equation for the reaction. I'll explain this, showing you this general reaction here, where the big letters, the capital letters A, B, C, D are the compounds, and the small letters A, B, C, D is the stoichiometric coefficient. So we can write the equilibrium constant for this reaction, the mathematical expression for the equilibrium constant, like this. We have the product is C and D, so the partial pressure of C raised to the little c power times the partial pressure of D powered to the little g power divided by the reactant, that is the partial pressure of A to the little a power times the partial pressure of B powered to the little b. This is a mathematical expression for the equilibrium constant for the reaction I've just showed you. Another information, when we're dealing with solutions, liquid solutions instead of gases, use the molar concentration instead of partial pressure. Let's remember that the molar concentration means the number of moles divided by the number of liters of the solution. And the symbol for molar concentration of a substance is this square brackets, and inside of the square brackets we use the substance symbol. Before we continue with the examples, I should mention you one rule. Pure liquids and solids are used in the K mathematical expression because they are actually equal 1. So let's see this example. We have this equilibrium of calcium carbonate, which is solid, and the product of the composition is calcium oxide, which is also solid, and carbon dioxide, which is a gas. So let's write the equilibrium constant for this reaction. So we have that calcium carbonate is solid, doesn't go into the equation, and calcium oxide, which is also solid, doesn't go in the equation as well. So we can write the constant equilibrium just by the carbon dioxide. So the equilibrium constant is the partial pressure of the carbon dioxide. Chemical equilibria with reactants and products that are in the same phase are called homogeneous equilibria. Equilibria in systems having more than one phase are called heterogeneous equilibria. One example of heterogeneous equilibria is this one, which we have in the side of the reactant sodium hydroxide, which is solid, and by the product side we have calcium, the ion calcium, which is in the aqueous phase, and hydroxide, which is in the aqueous phase. So we have solid and aqueous phase, two phases. So we have heterogeneous equilibria. The equilibrium constants for heterogeneous reactions are also given by the same expression we were studying before. There's no change in it. Let's write down the equilibrium constant for this reaction. Because calcium hydroxide is a pure solid, the calcium hydroxide must be present for the equilibrium to exist, but it does not appear in the expression for the equilibrium constant because it's solid, so that's 1. So to write down the equilibrium constant, we just have to write down the concentration of calcium multiplied by the concentration of the hydroxide squared because of the stoichiometry coefficient. That's all I want to say about this video. We will have some more videos for this playlist, and thank you for watching.